A decision is a selection from an admissible set, a choice of action that satisfies the structural constraints on the system. Optimization is a special case of decision-making in which a complete objective function is available, and the selection is the unique Argmax. When the objective function is unavailable, partially specified, or uncertain, the Argmax cannot be computed, but a decision can still be made from the admissible set. Optimization requires more information than decision-making and fails when that information is absent or wrong. Decision-making degrades gracefully. Any element of the admissible set remains a valid choice, even without an objective. The admissible set A defines which actions are structurally permitted, independent of any performance objective. Admissibility constraints encode hard requirements. Safety margins must be maintained, resources must not be exceeded, physical feasibility must be preserved. These constraints are applied before any performance evaluation. They filter the action space, not rank it. An action that violates an admissibility constraint is excluded regardless of its performance on the objective function. Admissibility is a precondition for decision, not a performance criterion within the decision. An objective function specifies what the system should optimize and can be traded off against other objectives through a Lagrangian or weighting scheme. A constraint specifies what the system must not do and cannot be relaxed in exchange for better objective performance. The structural distinction is fundamental. Treating a constraint as if it were an objective changes what is admissible and what is merely suboptimal. A constraint violation is not a suboptimal outcome. It is a transition to a structurally invalid state. System designers must explicitly classify requirements as either objectives or constraints before formulating any optimization problem. Optimization under a fixed objective tends to push solutions to the boundary of the admissible set, consuming all available margin. At the boundary, the system is maximally efficient under the assumed model and maximally fragile to model perturbation. A small deviation in the environment or objective can push the boundary solution into infeasibility, violating constraints that were satisfied at the optimum. Interior solutions sacrifice nominal performance but maintain structural distance from the constraint boundary. The trade-off between optimality and interior margin is a formal design choice, not a failure of optimization. Ensemble admissibility requires that constraints be satisfied on average over the probability distribution, but allows violations on individual realizations. Almost sure admissibility requires that constraints be satisfied on every realization within the support of the distribution. Optimization objectives are naturally evaluated in expectation. The Argmax of EFA, X, is an ensemble concept. Hard structural constraints, safety boundaries, physical limits, irreversibility conditions require almost sure satisfaction. Encoding a hard constraint as an expectation constraint is a structural error that permits unsafe outcomes under low probability realizations. Optimization requires a complete and correctly specified objective function, a full mathematical description of what the system should achieve. In complex engineered systems, this specification is often partial, uncertain, or subject to change after deployment. When the objective changes, the original optimum may become suboptimal or inadmissible under the new requirements. Decision-based design is more robust to objective evolution because it is defined by the admissible set, what is forbidden, not by what is optimal at a particular time. Any element of the admissible set remains valid as objectives change, as long as the structural constraints are preserved.